I'm Byung-woo and I'm from Computer Science in Chung-ang University. Today I'm going to talk about segmentation using a shaped-hire. And this may not be sophisticated enough to mathematicians, but like you. However, the main point of this talk is to motivate each of you to get interested in image analysis, especially in medical imaging field. So the objective of this work is to partition the regions of interest, especially in cardiac MRI. The images we are seeing here is slices of cardiac MRI in different phases. And the segmentation of, so the regions of interest in this cardiac MRI include epicardium and endocardium. So this is heart area, this is heart. And so this region indicates endocardium, and this boundary indicates epicardium. So the goal is to segment, that means partition these regions of interest in this image domain using the local statistics of images. So this image shows the example of segmentation results. So endocardium and epicardium, and actually MRI images has a 3D information. So actually that is surface, and the ultimate goal is to find the partition that gives the regions of interest in MRI surfaces. Okay? From the clinical point of view, this is significant in that the heart disease is one of the major serious common causes of death worldwide, including Korea. So the quantitative analysis of heart motion or heart parameter is crucial. That includes walk motion and diastolic volume and systolic volume and ejection fraction and so on. So that the clinicians are interested in measuring the volume of blood coming from the heart and coming out to the heart and so on. So that quantitative analysis is very important to clinicians, and it is quite useful in the diagnosis of heart disease. So the segmentation of left ventricle, as we can see, as we can saw in the previous slides, is very essential in this quantitative analysis. From the numerical point of view, it is quite challenging because the boundary of regions of interest is not definite or sometimes often very subtle. So we have to overcome such lack of information that defines the boundary of regions of interest. So we are interested in how to incorporate high-level visual cue into such low-level or middle-level visual tasks, such as segmentation. So here in this work, so I'm going to talk about how to incorporate shape information into segmentation tasks. And shape has been used as prior knowledge for a long time because shape gives a purely geometric property that is invariant with respect to a lot of imaging parameters such as illumination changes and so on, the surface properties. So the shape is quite useful information in order to incorporate high-level information. So this is a very famous picture, and I'd like to ask what it is, what is here in the picture. So some of you may know what what is here in the picture, but some of you may have very difficult time to find what it is. Okay. So if you look at this image very carefully, there is one dog, Dalmatian dog. So this is head, and the body and legs, and so on. So if you know that there is a dog, and that is a Dalmatian dog, and if this is a head and body and legs, then you can immediately recognize there is a dog in the picture. However, prior to you know there is a dog in the picture, it is really difficult to know what it is. So this tells you that the higher level knowledge or prior knowledge is very important in a lot of visual tasks such as recognition or segmentation as well. So this is a motivation that we'd like to introduce higher level information into low level or middle level visual tasks that include segmentation or recognition as well. So this is a list of related works. So basically, people have been trying to draw the boundary of regions of interest based on local image features such as texture or intensity, edge, and so on. So this is a local feature, the segmentation based on local feature. And people have tried to find the boundary based on the regions that is more robust with respect to local noise. And then the level set is introduced into the segmentation. So people have been trying to formulate the energy functional of segmentation in terms of level set function. So this is a list of related works, and some of these works are trying to find the boundary of objects that prefers a certain specific shape. So in this way, the shape information is integrated into segmentation. Then what is a segmentation? So some of you may be very familiar with a term called segmentation, but some of you may not know about segmentation. So let me briefly tell you about what segmentation is, what is the major objective of segmentation in this context. So goal of segmentation is give a partition of the image domain into meaningful area. So meaningful means you define. So it is up to the observer. So some of you may be interested in some specific pattern, but some of the others may be interested in different patterns. So meaningful means you define what that is. So the segmentation, so meaningful is a property that gives homogeneity of property, and the goal of segmentation is to give a partition of the domain. So let's denote omega to be the domain of image, and R sub I is the segmenting reasons. So the domain is represented by the union of subdomains. Okay? And the segmentation process is normally formulated by the partitioning function that is defined in this way. So you define a certain energy with respect to partitioning, and that is defined by the summation of penalty function that is on each subregion. So you try to minimize this energy function with respect to partitioning using certain energy. So in a Bayesian formulation, in a probabilistic framework, we can express this segmentation process in this probabilistic setting. So like to maximize this probability of partitioning function given image. That is exactly equivalent to this likelihood function, that is a conditional probability of image given partitioning multiplied by prior, that is the probability of partitioning function itself by Bayes' rule. Okay? And this likelihood function can be represented in this form. And we simply assume their independence. So it can be represented by the multiplication of each probability on each subreason. And the last prior information on partitioning function can be simply given in this way. This means that it penalizes the length of partitioning, where C represents the partitioning curves. Okay? So it prefers the shorter curve for partitioning. Then we take negative logarithm and we define energy using in this form. So we like to minimize this energy with respect to partitioning. Then now we come up with the question, how to define this probability? So a lot of people have been trying to formulate this probability in different forms. So in the previous lecture, Osho told us about many different image models, the energy models, that is also related to this probability. So now I'm going to talk about one of the most popular image segmentation model, that is called Mumford-Shah model. This is not amazingly fast like L1 norm. So this uses L2 norm, so not that fast. But this is one conventional segmentation model. So if you look at this energy form, then at this input image, U is piecewise smooth. And C is partitioning function. So this means that of a given image, input image F is approximated by a piecewise smooth image. Okay? So this is a data fidelity, and this is regularization by total variation. And finally, we prefer to have a smooth curve as a partitioning result. Okay? But this is one of the disadvantages of this energy formulation is that it is very difficult to minimize with respect to curve C, because this should be minimized with respect to unknown C. Okay? So most simplified version of energy formulation was introduced. So in the limit, lambda goes to infinity, we can have a piecewise constant instead of piecewise smooth image. So this is a piecewise constant model when lambda goes to infinity. So we have an energy with respect to the partitioning curve C. And given image F, we have a piecewise constant Ui. So Ui for each sub-reason on I. Okay, and finally we have a regularization again. So this is more simplified segmentation model, assuming the image is piecewise constant. And then we come up with a question, how to represent this curve, partitioning curve for segmentation. So here we are going to represent a partitioning curve using level set function. So one advantage there are many advantages of using level set functions, but one major advantage is you can deal with topological changes naturally. Okay? So if you have an explicit representation such as a list of points, then it's really difficult to deal with topological change from a single topological curve, from single curve, single circle, for example, into two circles. Okay? But it's very natural to represent such topological change using a level set function by evolving the level set function. Here, the curve is represented by 0 level of level set function. So let me go more faster. So this is a very popular model that is called Chung-ang-based model that assumes the piecewise constant using one phase, single phase. So this is a bipartitioning function, and this is a front evolution, the equation for that one. And we're interested in modeling this prior probability using explicit shape. So as we have seen in the first slide, we are interested in extracting two boundaries of epicardium and endocardium. Okay? And they look very similar, not identical, but similar. So we would like to define the shape similarity between two curves using level set functions. So the one curve, if one curve is represented by one level set function that is by 1, and the other one is by 2, then by 2 minus by 1 exactly tells you the distance from one interface to the other if it is a perfect circle. If it is perfect circle, then the value of d at every point within this region, restricted region, tells you exactly the shortest Euclidean distance from any point in one shape to the other. However, it is not perfect circle. For example, circle and rectangle, that it is not constant in this region. So we model this shape similarity using this Gaussian distribution, meaning that it follows this Gaussian distribution. Okay? So finally, we model the segmentation energy using data fidelity, using piecewise constant model and regularization for two curves, and shape measure, that is the shape prior. Okay? And this is the final energy functional that consists of data fidelity, regularization, and shape prior term. Then we have a parameter for modeling shapes that is mean and standard deviation. Then if you look at this image, we have two curves. If you apply Chung-ang base, then we get these results. But introducing shape prior and with a very small standard deviation, that means two shapes should be very similar. If you allow more variation, then it is more rely on the data fidelity. Okay, so you capture more data instead of shape similarity. Okay? And this is the final results on real data. So this is annotated by radiologists, and this is automatic detection. And this is the same. So the ground truth and detected by the algorithm. And in 3D, this is a final segmentation in 3D. So let me finalize this talk. So it is sometimes essential to introduce higher level information, such as shape in segmentation. And there are a lot of applications in medical domain, and we will encourage you to get interested in this area. And thank you very much for listening.